Добрый день. Я сразу отсюда начну, поскольку мне все равно.
Good afternoon. I will start from the rostrum because I'm the first speaker anyway. So according to the agenda, we have a nap hour after lunch. And so in this quiet manner, not to awaken anyone who doesn't want to be awoke, we'll be discussing ammonia, urea, fertilizers, trends, and outlook. I guess this will be a very versatile session. And I'm here not because I'm moderating, but because I'm the first speaker as well. And next, I will give the floor to representatives of companies which are technology providers and process providers. They have interesting stories. Right after me, Alexandra Karyagina, Chief Licensing Manager, Moscow, Gas Chemistry and Oil Chemistry of Haldor Topsoe. Alexandra has been with HT for many years. I don't believe we should do any kind of introduction for HT. They're leaders in terms of ammonia and catalyst technology. Alexandra is the graduate of the Gubkin Oil and Gas University and was with various companies. And for many years, she's been with Haldor Topsoe. Then over to Boris Kalashnikov, graduate of the Moscow Aviation Technology Institute, engineering technology in polymers and composites. He did the postgraduate study in the Moscow Academy of Chemical Engineering, specializing in separation of liquid unhomogeneous liquids. At the moment, he covers syngas units at Linde Engineering. And the final speaker in today's session is Oleg Kostin, graduate of the Nizhny Novgorod Lobachevsky University, specializing in chemistry since '91, has been at various leading positions in engineering companies. I know you know what the company is. Then he came to work with a different engineering company. It's a surprise for me. He's now with GIAP. Oleg made it to GIAP in 2001 as the General Director, Deputy General Director for Commerce and Development. And prior to that, for many years, he had been leading projects for ammonia, urea, and methanol. And I am Georgy Eliseev, Ammonia Analyst at Ferticon. I guess you know what Ferticon is. The audience knows well what it is. We're now part of IHS Markit, a well-known brand, but primarily covering energy, oil and gas, and petrochemistry. And the fertilizers segment is now part of the IHS Markit family and their coverage. I joined them in 2019. I am based in Moscow, and I cover the publication which is called Ammonia Outlook. That is a quarterly product with the analytics of the ammonia market and forecast. Prior to that, for 10 years, I had been with Russian chemical companies, primarily in fertilizers. But let's skip over and right to my presentation. Today, my talk will focus on green ammonia or carbon-free ammonia. Many of our subscribers take quite in-depth interest in that, even though our core business is existing markets of ammonia and other products. And yet, since the issue of decarbonization is an acute one in today's worldwide agenda, and there is great degree of interest towards it, not just in our industry, but in many other segments of the economy where ammonia could be put to work. Thus, we do the talk. So the contents of the presentation, first of all, terminology, gray, green, and blue ammonia. Then there are several layers of issues. First of all, there are issues of decarbonization of existing industry of mineral fertilizers. That is more than 1% of the worldwide carbon emissions. So we are under pressure in the industry. Or rather, the industry is under pressure, and steps are being made in some projects concerning green ammonia for fertilizers are being implemented. Then there are absolutely new areas of application of green ammonia. First and foremost, this is hydrogen-based power generation, where ammonia could be used as a tool for storage and transportation, and alternative to hydrogen, meaning type of fuel, which could be used, for instance, in marine-going vessels, which is a popular topic nowadays. And finally, we try to make a forecast for the ammonia market, even though now we have no data whatsoever to make a scientific forecast. But at the level of speculative forecasting, we shall throw in a few comments as to the share of carbon-free ammonia by 2035. So, starting with definitions, this is what is called now gray ammonia. That is the classic process of making ammonia from hydrocarbons via steam reforming of methane and synthesis under the well-known process. In the synthesis of ammonia, we require hydrogen and nitrogen, and the carbon which makes it in together with hydrocarbons is a waste product. In more than half of the cases, it is being recovered and then returned to make urea. But when urea is consumed as a solution for some industrial needs or a fertilizer, well, all in all, this carbon ends up in the air. So utilization of carbon in urea is not counted as proper utilization of CO2. So that's why we have about 1.8 tons of CO2 emitted typically as the result of this process. At some production sites, it is more than that. In others, it is less than that. It all depends on the energy efficiency of process units, the technology employed, upgrades, generation of technology, and the variations are quite wide. If we have coal-to-gas processes, it is even greater, as opposed to using natural gas as the key feedstock. So what can be done in this regard? This technology is not novel. It's been around for many decades. We can take water, and via electrolysis, we can separate hydrogen and oxygen and use the hydrogen for synthesis of ammonia together with nitrogen. And we need to put in place an air separation unit to make nitrogen. Considerable developments in the recent 10 years have been associated with energy requirements for this process. Improvements are great. 10.5 megawatts per hour is required now to run this process and to make sufficient amounts of hydrogen for 1 ton of ammonia. And the technology advances further, and there are even bits and pieces of information that some pilot units can consume less than that, about 8 megawatts per hour. What's also important, in the recent years, the cost of green energy has been decreasing. The electricity required for the process is, of course, green energy. That is wind, solar, biomass, perhaps hydro. And in the recent, I would say, 5 years, the cost of megawatt hour of electricity of this green energy went down to the level of conventional fossil fuels generated power. In Europe, they say that 1 megawatt hour might be about €40. In North America, about $40, a bit less than in Europe. If we require 10.5 megawatt per hour, then just sheer electricity would cost about $450 per 1 ton of ammonia, which at the price of $300, which we saw not very long time ago, would mean that this process is not economically viable, to put it mildly. We have such preliminary estimates of green versus gray ammonia, capex and opex gaps for hypothetical output of green ammonia. It is not yet available apart from pilots. Compare it to existing Europe-based gray ammonia. And the prices we took were about $4 per MMBTU of last year. Even if we add to this cost in Europe the full cost of emissions under the pricing of European trading systems for emissions, and you know that ammonia producers don't pay the full amount, they only pay for going above the benchmark volumes. Still, the production cost for green ammonia would be about double as opposed to those for gray. There are expectations of further advancements in process technology and consumption of power decreasing per 1 ton of green ammonia. So the cost associated with the need to put this hydrogen into the reactor of Hydro-Bosch, where we require both pressure and high temperature, and perhaps using some novel catalysts might bring down the associated costs. And perhaps some more radical changes. For instance, an Australian university has published research on the possibility of a one-step scheme of making ammonia, whereby ammonia would be the output of the electrolysis phase, no Hydro-Bosch. And they say that in 4 years they will be ready to do the pilot. Well, something of the kind can shoot up and change the situation drastically. Insofar, it's apparent that apart from political support and without any kind of coercion policies to make consumers opt for green ammonia and some kind of stimuli, this green ammonia won't fly in the free market context. It wouldn't survive the competition with the gray, but some forecasts say that in the middle of the 30s, due to various reasons, its cost will be competitive, including higher costs associated with conventional processes and higher prices for natural gas, which we forecast. And in addition to that, because of the use of the emissions trading schemes and high price for emissions. There is one more option, blue ammonia. Notionally speaking, the difference from gray is that CO2 is recovered and is not used for making urea, but rather utilized in some way, either re-injected in some geological formations, subsoil, or re-injected into the productive reservoir for crude production enhancements, or made into some liquid or solid products which are not CO2 emittent. Perhaps it's a temporary solution for the time it requires for the green technology to mature and the costs to be reduced, because it is not carbon-free, it is low-carbon ammonia, because still some kind or some quantity of carbon might escape. And the key point is that all ways of utilization are not very perfect. Here I throw in specific cases, ways of utilizing CO2. There are projects in the US at Wabash Valley Resources in Indiana, 550,000 tons ammonia and a CCS plant and reinjection of CO2 into the geological formation. This topic is well known, and every project would have a resource to reinject CO2 under pressure or in liquid form, and it might be good for hundreds of years. But our planet is not a soccer ball, and it won't work if we pump it with CO2 endlessly, and I guess there are quite a few limitations there. If you need to transport the CO2 to the point of injection, and the transportation leg is long, then the solution is not the best option. Next option is enhanced oil recovery, a well-known way used since 70s to enhance production at depleted fields. The flaw of this approach is that when you pump it into the reservoir, you extract just as much carbon, but in the form of hydrocarbons. From the point of view of decarbonization orthodoxies, that is not the cleanest way. And since Russia considers it as the key area of development, there are high risks of someone finding it that this ammonia is not carbon-free if one reinjects into the reservoirs. There is the reverse process when CO2 is converted to CH4 or syngas, but for that purpose hydrogen is required, so it doesn't work for us. There is a project in the States called Monolith where CO2 is converted in solid carbon, so that is steam cracking, and then solid carbon is used for various purposes. There are other ways to deal with CO2, such as conversion into chemicals, such as graphite, perhaps diamonds, artificial diamonds. I guess fertilizers producers would be willing to trade in diamonds. Well, in any case, all that is associated with limited markets, and one won't have the option to sell in large volumes. But say Saudi Aramco uses CO2 instead of methane for making some chemicals. I guess chemical industry can come up with quite a number of options to use that in various organic compounds. The flaw of that is that all those chemicals towards the end of their life cycle might end up in some dumping sites, and carbon would escape again into the air. It could be used to reinforce concrete, but the cement industry is a largest emitter of CO2, so I guess they would cover that niche. Nanotubes or nanofibers, and an interesting solution which we see in nature, photosynthesis consumes carbon and turns it into elements of soil. Now they're investigating as to how this process could be sped up, and perhaps that might lead to a breakthrough. So that's an ingenious solution. Mineral fertilizers producers will be making artificial soil, input the fertilizers in there, and sell the final product, enriched soil. So all producers of ammonia are feeling the pressure now and have to come up with something to address their issues, develop some programs, establish some goals, and establish some deadlines. So to end up greenhouse gases emissions. There are various responses on the part of the industry in Europe to a great extent that has been described by the current policies. That is the new stage of phase 4 of the carbon trading system, lowering the benchmark, which comes free of charge. Until recently, they could emit 1,619 kilos per 1 ton of ammonia. If they did above that, they were to buy credits in the ETS system in Europe. The prices in Europe were quite low for many years. If 1 ton of credits would be about 20 euro, and they needed to buy 150 to 200 kilos, so 3 to 4 euro was all it cost for them for carbon emissions. Comparing it with $400 or $500 per ton, it is clear that that was not a major impetus for them to change anything. And yet we see now that, first of all, the benchmark starting this year will be 1,575 kilos, and that is on the verge and even below the level that modern technology can afford. And that means that costs will be rising, prices at the ETS system will be rising. It is already more than 40 euro. If the demand for quotas will be rising, the prices will be rising further. And we do see that several European producers have already started to pursue such a policy as construction of quite small units of green hydrogen. This year, they are to launch the first of such units in Spain, in Portellana, where Fertiberia will be consuming 10% less of natural gas, ousting that with green hydrogen, thus decreasing by 10% the average CO2 emissions, which would make them fit into the current benchmark. There are several such projects with Yara and other producers. We believe it is also inevitable, and it is under development now, that is the protection of this market and other markets which would feature same kind of measures and stimuli. Protection from leakage of carbon. I guess it is not protectionism, because ammonia producers in Europe themselves, and the same goes for steel, cement, and other industries emitting carbon, all those suffer much more. So, figuratively speaking, European legislators, after raping their own producers, they can't leave them alone when cheap producers of ammonia from countries with cheap natural gas, such as North Africa, Middle East, and Russia, might oust them from their own market because of low prices for their products. Therefore, inevitably, there will be a kind of barrier, and it could be designed in various ways. According to our data, the European Parliament is discussing it now, by the way. Those measures, most likely, that will come as a kind of duty, which will be linked to the price of 1 ton of emissions in the ETS system. Another issue as to whether we have this green energy for decarbonization of the industry. And we don't have lots of it. If we add up all the biomass, solar, wind, power generation capacities for switching entirely to green ammonia, we would need about 67% of that capacity. For 1% of cutting carbon emissions, no one would give 67% of green energy. At some continents, it is way above 100%. Looking at this map, if it is if you look at Eurasia, if you want to ask me about the chances for green ammonia in Russia, we have nothing to make it from, no chances whatsoever. We need to catch up with other continents. That's a typical situation for regions which are well endowed in hydrocarbons, where hydrocarbon fuels will always be cheaper and alternative energy could not compete with those point blank. Another issue of importance is what do we do with urea? I guess we have a lot of people here which have to do with urea production and urea production processes. There is an opinion that in the bright carbon-free future, there will be no urea, there will be nothing to make it from, because the flow which we got from the ammonia process would be reinjected in the subsoil instead of using it for making urea. What do we do in terms of farmers in India, China, and other nations consuming dozens of millions of tons of urea, and what it could be replaced with? In Europe, they're using hydrates. In agriculture, they have a standing tradition of using that. On other continents, that might be an issue. On the one hand, it means that there will be many years to come of gray ammonia. No one will surrender it just like that. Secondly, it means that there will be a certain kind of movements, perhaps developments in the green urea, making it from biomass, because biogas is quite rich in CO2. And together with green ammonia, one could make carbon-free urea, having in mind that biomass is made of plants which consume CO2, so we return CO2 back and do not increase its contents in the air. There is a big risk associated with that, because we could run it in the spiral. An accelerator kind of arrangement will require more urea, and for that we need more biomass, and to make more biomass we need more urea, and so on and so forth. And we know that looking back in history, we have cases when making technical, growing technical plants was detrimental for growing foodstuffs, because local landowners were after profits and not after feeding their own population. There is quite a number of production projects for green ammonia in the industry. They break down into three groups. One is only one group, Yarrow, in Norway, which declared that the entire plant, when there is enough green energy available, could switch to electrolysis. There are several projects I mentioned whereby you just attach a small production of green hydrogen to the existing process to make the average CO2 emissions lower. And group 3, for instance, Morocco-based projects and Chile-based projects, importers of ammonia. At the same time, they have lots of sun, and sun energy, especially at high elevation where radiation is good, could be efficiently used for making ammonia on the spot, hosting quite large volumes of imports.
Как бы завершая, несколько слов скажу.
And wrapping up, just a nutshell comment. One could use ammonia as the carrier of hydrogen, because there will be regions in the world where it makes more sense to develop green energy, and from there green energy should be transported to pockets of consumption. It's not clear what one would do about that, and one of the options is turn it into ammonia and transport it further and basically convert it back to hydrogen, or use it directly as fuel, or as a mechanism of storage of energy, having in mind this cyclicality, a large amplitude model of consumption of electricity. And sources of green energy are not manageable, they are not sustainable, and require some efficient storage solutions. So ammonia could be used just in the course of the day. We make it in the morning and we burn it in the evening to use this energy. In this case, the cost of ammonia is not important, because what matters in this case is the amount of energy you can bring back into the system. If the generator is happy with the return of energy into the system, this mechanism could work. And there are quite a few projects which have to do with generation, green, blue projects, and so on. And the last comment on my side, in the marine transportation, they seriously consider using ammonia, which contains no carbon whatsoever. IMO, International Marine Organization, has decided on the goals to have not only low carbon types of bunkers, but also carbon-free types of bunkers. So far, it could only be ammonia. No other options are on the surface. There are, of course, quite a few flaws, but this topic is being further considered. And what is interesting, last year, production and consumption of ammonia, gray ammonia, was about 190 million tons, with a capacity of 220 million. If we account for the current amounts of bunkers and oust only 25% by ammonia, we would require 240 million of ammonia. And by 2050, marine traffic will be up, and it will be up by 250%, which is quite an option. Having in mind the growth rates, we would require 600 million tons of ammonia just to cover 25% of marine transportation. What if it is 30 or 40, or some inland waterways consumption or rail consumption and other areas of consumption? We can easily hit more than 1 billion tons of ammonia. That is 5 times of from today's existing capacity to meet those energy requirements. And it is apparent that next door to the existing industry, there could be another industry, a much larger one, which focus on the absolutely novel ways of demand for ammonia. And the very final slide, we speculatively believe that as soon as 25, we'll have 1.5 million tons of capacity, some 5 million tons by 2030, and by 2035, from 20 to 30 million tons, which is in line with 10% of the worldwide output. And of course, a great role in this context will be played by the support of this green industry through 2035, when it might finally become competitive. Important consideration is availability of independent audit of carbon emissions. So far, it's not clear who and how will be judging upon the color, so to speak, of your ammonia, green, blue, gray, in terms of decarbonization. So thank you so much for your attention. I'm wrapping up my presentation, and perhaps later on we'll go back to that topic via questions. Now, over to Alexandra.